At this point, you're knee deep in derivative rules. Did you know you're eventually going to be shoulder deep in derivative rules? And you also understand the concept of a tangent line representing the slope of this curvy function at a specific point. You even know how to build a tangent line, but the tangent line is such a big shot in the world of calculus that we need to get even more expert at it, and so we're going to take a deeper dive into tangent lines, which is also very intertwined with derivatives. So we're going to start with this somewhat friendly parabola. And what we want to do is we want to find the x-coordinate of any horizontal tangents. Horizontal tangents will come to be very famous in calculus. Some would say even more famous than Johnny Cash. That's a bold statement. Well, if I want to find a horizontal tangent, the thought going through my head is a horizontal tangent. Let me draw one for you, by the way. If we have a parabola doing its thing, the horizontal tangent is the spot where the tangent line has a slope of 0. So that's exactly what I'm going to think to myself inside my brain. I'm saying, hey, when is the slope 0, which is when is the derivative equal to 0? Okay, well, that's not so bad then. I'm going to just take that derivative, and you know the power rule, so 12x minus 2, the derivative of a 7 is a 0. So there's my derivative, and I want to set my derivative equal to 0. So this is math talk for my slope is equal to 0, or in other words, horizontal tangent. Now I solve for x, that's going to be darn easy. X is 2/12, so I'm going to reduce to 1/6. So at x equals 1/6, I have this phenomenon happening. Now, by the way, I could also plug in and get a y value if I wanted to, but I don't feel like plugging a 1/6 into that mess. Finding a horizontal tangent means first derivative equal to 0. So yeah, first derivative equal to 0, and you should probably become pretty darn good at that. Let's look at this next example. You'll notice in this next example, we start with dy dx. In other words, there was some function y. I don't know what it looks like, so y equals blah, 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 blah. And when we took the derivative, we got this monster right here. And that will happen later on in the year, but also this is the type of thing the AP test writers sometimes do. They will give you a derivative, letting you off the hook from finding that derivative, but then seeing if you can do good stuff with it. So we want to find the x-coordinate of any horizontal or vertical tangents. So I chose this derivative on purpose because remember, if it's a horizontal, that means the derivative equals 0. And in this case, since we have a fraction, remember that any fraction in the world equals 0 when it has 0 in the numerator. All of these fractions equal 0 because they have a 0 in the numerator. So if I'm wondering when does my derivative equal 0, or when do I have a horizontal tangent, it's as simple as saying when does my numerator equal 0. So to find a horizontal tangent, I will take the numerator, set it equal to 0, solve it, and now I know x equals 1/2 is the location of a horizontal tangent. Now we're going to head back to Algebra 1 for a second. When you think about a vertical tangent, what's happening there is your function momentarily is going straight up and down. So it's hard to draw this accurately, but at that spot, you have a vertical tangent. In other words, your slope is undefined because any vertical line, if you remember from algebra days, anytime you had a vertical line, the slope was undefined. So how do I get a undefined out of a fraction? It's when you have the denominator equal to 0. So if you think about this, if you have the fraction 5/0, negative pi/0, any of those lead to an undefined value. So if I would like to know when my derivative takes on an undefined value, I worry about the denominator equaling 0. So I do this equation. Now I have to break out a little bit of trig, little unit circle knowledge, and I didn't set a domain for this problem, so let's just take any value on the unit circle that equals 1/2. There's my trusty unit circle, and I'll say pi over 3, but there's really more than that. So if I had a graph of the equation that gave birth to this derivative, I would spot a horizontal slope or horizontal tangent and a vertical tangent at those locations. This means when you see a fraction in your derivative, you might actually be happy because it does make your life a little bit easier. Okay, I've got 2 more examples to go. In this example, we say at what x-coordinate are the tangents to g of x and h of x parallel? So both of those are curvy functions, they're both quadratics, and we're sticking with equations right now that lend themselves to the power rule because we don't know a lot of other rules, but we could eventually replace these with sines and natural logs and e to the x and all that good stuff. Well, if we're going to have the tangent lines to these 2 graphs being parallel, that means they both have the same slope, which means they both have the same derivative. So the big picture that I would like to do is say, hey, when does g prime of x equal h prime of x? When is the slope of g equal to the slope of h? Well, I'm going to do my derivative with power rule. That's 2x plus 2. I'm going to do my derivative with power rule. That's 6x plus 10. And now I can go ahead and solve that. That's a 4x over here and a -8 over there. X equals -2. I made that look fast and easy, but it would take some brain power on your part, especially in the beginning of your calculus career. So at x equals -2, this graph and this graph are running parallel to each other for just an instant moment in time. I'm going to do one more example, and it's not going to break any new ground, but it's going to show you how hairy and gross some of the calculations can be. I'm going to pause this while I set it up. Okay, here's the problem. We're saying at what x-coordinate is function g parallel to function y? Now we have a trig function in here, and you may not know trig derivatives yet, but don't worry about that. I'm going to just show you both of these derivatives before we get started. dg dx, the derivative of equation g that happens to use equation x, we'll find out someday that this has the derivative of positive sine of 2x times 2. And then we have dy dx, the derivative of equation y that happens to be using variable x. That has a derivative of square root of 3. That's power rule, although it looks a little clunky. So if these two are going to be parallel, then I'm going to put this coefficient of 2 out in front. We deserve that. We deserve to be treated with respect. So there's my equation. Basically, the slope of function g is equal to the slope of function y. And remember, the purpose of this one was to show you how hairy these calculations can get. So I'm going to pause this and work out my work. If you were smart, you would pause it and work out your work. And then when we both come back to the video, we'll compare. So go ahead and do it. Pause it and work it out. I'm back with some ugly calculations. By the way, I didn't really give us a specific domain, but that's not going to matter. You can see from, you could pause this thing and compare your calculations to mine. But at some point I had to get rid of the sine by using the inverse sine, or I could have used arc sine, same thing. And then I eventually solved for x being pi over 6. And the way I do that, by the way, when I had the inverse sine of square root of 3 over 2, I selected this spot, pi over 3, because pi over 3 is when sine has a square root of 3 over 2 value. So the example here was just to show you these calculations can be crazy. See ya.